Good day and welcome to another episode of our lecture. In our last lecture, we were able to identify the four quantum numbers, the principal quantum number, N, the azimuthal or Sommerfeld quantum number, L, the magnetic quantum number, N, and the spin quantum number, S. Now, today we are going to look at the rules governing filling of an electron in an orbital. The rules governing filling of an electron. At the same time, we're able to identify, that is when solving the Schrodinger and Dirac equation, we are able to identify four types of orbital: the s orbital, the p orbital, the d orbital, and the f orbital. And now let us look at the rules governing filling of this orbital. People like Aufbau stated in his principle, it states that electrons are added progressively to various orbitals in the order, very important, in the order of the increasing energy. That is, you don't jump into a higher energy leaving a lower energy. You have to start from a lower energy progressively down to that of a higher energy. Like in this format, we have you fill in the 1s orbital before the 2s orbital. You fill in the 2s orbital before the 3s orbital. Down, you fill in the 3s before the 3p, and down to the sp. That's what the Aufbau said. That is what Aufbau principles is all about. Now, the second principle is that of Pauli exclusion principle. Pauli exclusion principle states that no two electrons in an orbital have all the four quantum numbers alive. What are the four quantum numbers? The principal quantum number N, the azimuthal quantum number L, the magnetic quantum number M, and the spin quantum number. No two electrons in an orbital have all the four quantum number alike. That's the same. The next rule, principle governing rules governing filling of an electron is the Horn's rule. The Horn's rule, we've stated that of Aufbau, we stated that of Pauli. The next one is Horn's rule. The Horn's rule of maximum multiplicity states that the electron in a subshell S, P, D, and F occupy orbital singly before pairing. It's occupied, that is, if the electron is in any of these subshell, it occupies singly before pairing. Let us take an element like oxygen. The atomic number of oxygen is 8. Automatically, it has neutral oxygen has 8 electrons, which is, when you're filling it, you start from the lowest, 1s, the maximum is 2, 1s2, followed by 2s, the 2s, 2 maximum, remaining, that is 2 plus 2 is 4, remaining 4. The 4, it goes to 2p4. The 2p, the maximum the p can occupy is 6, and therefore we have 4 here, is in order. Then these 4, how are we going to arrange them? That's what Horn's rule is all about. We have how many types of p? We have the px, the py, and the pz. Horn's rule said it has to occupy, the orbital the electron has to occupy each of the orbitals singly. Okay? Singly, like this, singly, before what? Pairing. Since we have all the px, the 4 will not just go into here, that least, like this, no. It has to occupy it singly, 1, 2, 3, before pairing. This is before, this is after. That's the rule. It has to occupy singly, then before pairing. This is the pairing. The pairing will go to the 4x. It has to go, and it has to be of a different spin. It doesn't have to be of the same spin. It has to be of a different spin. It has to be of different spin, as stated in this, as captured here. That is for oxygen, and so many other, nitrogen. It continues in that format. Now let us just take some few examples of how to write the electronic configuration. For example, we have our sodium here. The atomic number of sodium is 11. You can easily write it like this, following the energy, the Aufbau principle, the rule, starting from the lowest, 1s2, 2s2, 2p6, and 3s1. 1s2, 2s2, 2p6, and 3s1. And you now come that of potassium. The atomic number of potassium is 19. You have 1s2, 2s2, 2p6, 3s2, 3p6, that is 2 plus 2 plus 8, that's 8, and 4s1. Altogether, we have our 19. And we'll now go to calcium, which is 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. And when you look at it, the chemistry of some of these things, the outermost electron determines the position of that element in the periodic table. In the case of sodium, the outermost electron here is 1, therefore sodium is in group 1. In the case of potassium, the outermost electron here is 1, so that potassium is in 2. In this case, calcium is 2. The elements, calcium is in group 2. But however, there are some exceptional cases like that of helium. Helium is in group 8, it's not in group 2, because helium succeeded in completing that shell, the duplet configuration. It's duplet configuration, and it doesn't behave like any of the metals. Helium is a noble gas, so it behaves like more of the noble element than group 2 element. So also is hydrogen. Hydrogen is in group 1 because it has 1 electron at its outermost shell. In our next lecture, we'll be able to take a very good look at the periodic table and do justice to the elements. That is, we'll be able to write our ionization, and I will be able to define our ionization energy, the electron affinity, the atomic radius, the ionic radius, and their variation down the group and across the period. Thank you for listening.